single responsibility principle, which is standing for the S in the solid design principles, essentially states that a single module or class should be responsible for a single piece of the functionality of the system, which is commonly related to that to do a single thing. But the question is then, of course, what is a single thing? Today I want to give you a short explanation which I find very useful, which essentially is Robert C. Martin's explanation, the guy also known as Uncle Bob. And essentially he rewrites the principle as such. So he says that a class or module should have a single reason to change. Now this wording is not massively different, but it's slightly different, nuanced. So he talks about having a single reason, right? A cause of having to be changed, instead of the idea that the class or module should do a single thing. So in that sense, Bob Martin talks about what happens to the class in the future, whereas the single responsibility is traditionally stated in terms of what it does currently. I will just slightly borrow one of his examples because I think it's very useful in understanding how to sort of slice the pie in what's to be considered a single unit. So he gives an example along something like the following lines. Assume that you have a system, and then think about the different people that can come to your desk and ask you for changes that they want to impose on the system. So think about then what working roles these people have. So if, for example, say it's kind of like an accounting system, it's a bookkeeping system online, right? So you might have a lot of financial reports. So a designer might come to you and ask you to redesign a particular piece of a form, right? So move this entry field here and move this label field here and change the color of this thing and blah, 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 right? But a person from finance might ask you to add completely new fields. For example, might ask you to add a new calculation. Say that there's the law changes and now suddenly all reports need to include such and such a number. So thus they ask you to include that number. Right? There are overlaps here, of course, right? In adding the number that the finance guy asks you for, of course you have to also perform some design. But the point is that these are different reasons. It's entirely possible that you add the new finance calculation, you implement the change that the finance person is asking for, and that the designer is completely happy about that, right? But of course this reason is very limited to the idea of work roles and people coming and asking you for changes. But if you're building your own, if you're running your own product, if you're a small startup, or if you for some reason don't actually interact with people who can give you change requirements in such a manner, then you of course have to envision these incoming change requests yourself. You have to say, how would we potentially want to change this in the future? You know about startups, for example, there's the concept of pivoting, right? So then you think, how would we potentially want to pivot in the future? If the idea is, for example, we're currently doing this, but potentially we could be doing that, right? Then that would be a reason to change. Changing from the first thing to the second thing would be a reason to change. So that change needs to be isolated somewhere. But let's generalize a bit. I'm not saying that you always have to think about work roles when considering whether you're adhering to the single responsibility principle or not. But I find that wording, the wording a single reason to change, extraordinarily helpful. So think about it from this perspective. Another way to sort of slice the pie would be to say that when something happens in your system, or the order of how things happen, or why something happens, right, is not necessarily the same thing as how that particular thing happens, right? So why and when something happens is not necessarily the same thing as what the thing is that happens. So in terms of change, that would mean that it's not necessarily so that the order of the events changes at the same time as the contents of the events, right? I myself am currently working on simulations, so the order in which certain events happen in the computer simulation can change independently of how they actually happen, right? So assume we're simulating ecology and we have a bunch of animals, and we put them into some natural habitat, and then the animals perform different things, such as eating and sleeping and drinking and hunting and whatever. So the order in which we simulate these events could change independently of what those events actually constitute. So I'm pushing this example, but the point is that has nothing to do with roles, right? Working roles as in a company. But it has everything to do with having different reasons to change. We might, given our domain that we are in, right? Given the thing that we're building, the thing that we're modeling, it's entirely plausible that we would want to change the order of things without changing the contents of the actual things, and vice versa, of course. So that's all I wanted to say about Bob Martin's explanation of the single responsibility principle. I'll link some of his videos in the description, so be sure to check that out. And if you have other good explanations or ways to think about the single responsibility principle, I can go ahead here, and so shoot me a comment, and I would love to do another video on that particular way of looking at the single responsibility principle. That's it for me. Thanks for watching, and subscribe for more. Welcome to this series on the solid design principles, right? The SOLID, the solid design principles of object-oriented programming. So S for single responsibility principle, O for open-closed principle, L for Liskov substitution principle, I for interface segregation principle, and D, dependency inverting principle. Facilitate me. But today we are going to talk about the L here. L as in Liskov's substitution principle. And if you've ever read about it before, you're like, well, just reading the name Liskov's substitution principle, it's kind of like an instant brain explosion. You're like, who chose the word substitution? Substitution principle, like what's even the principle of substitution mean? But actually, if you dig down and you try to start to understand the substitution principle and you calmly try to just read it and think about it, it's actually very simple, and then once you get it, you're like, but isn't this blatantly obvious? Which it kind of is, right? But the thing about this substitution principle, which I find particularly interesting, is that it's one of these things in programming that are very, very well defined. Like, there is, we'll read it in just a moment, there is a logical definition of what strictly it means for something to follow Liskov substitution principle. Now still, there's a lot of room for interpretation and semantics, a lot of room, we'll get into that. But still, at least there is a rigid definition, which for many things are not, right? Like, single responsibility principle, for example, right? Like, what does even doing a single thing mean? Like, that's super up for interpretation. Very, very much up for interpretation. And even though there's interpretation, or room for interpretation in the substitution principle, there's less room for interpretation. So let me just write the name here. What we're talking about is Liskov substitution principle. This is what we're talking about. Liskov substitution principle. And clearly, the person who invented the Liskov substitution principle was named Liskov. Let's read the definition on Wikipedia. So prepare yourself for another mind blow. Substitutability is a principle in object-oriented programming, stating that in a computer program, if S is a subtype of T, then objects of type T may be replaced with objects of type S. In other words, an object of type T may be substituted with any object of subtype S, hence the name substitution, by the way, without altering any of the desirable properties of T. Correctness, task performed, etc. Right? Like, okay, so I have to know logic, and I have to know, like, use this strange notation of the S's and T's and types and whatnot. Stick with me, it's actually pretty simple, we'll talk about it. And then there's this other sentence that says, more formally, the Liskov substitution principle is a particular definition of a subtyping relation called strong behavioral subtyping that was initially introduced by, here it comes, Barbara Liskov, hence Liskov substitution principle, in 1987, actually in a conference keynote address titled Data Abstraction and Hierarchy. that was given, this keynote was given in 1987. Maybe it was more in 1987. Booyah! Okay, anyway. Here's the really interesting part. You know I said it does allow for some wiggle room or some room for interpretation. Here's that interpretation part. It says, this is, or it is, a semantic rather than merely syntactic relation because it intends to guarantee semantic interoperability of types in a hierarchy. And actually, here's the principle in the way they formulated it in a paper that Liskov and then somebody called Annette Wing published. And this definition is actually not that strange, so let's start in that end. It's a bit like logic heavy, so you have to put your like scientist hat on and go, okay, I shall now read logic and I shall not be intimidated by it. But let's go. Let me remove this stuff. So here's the quote from the paper. It says, here's the subtype requirement. Subtype requirement. So they're saying, what if there is some property provable of some x? Let this made a hypothetical pretend property, that's property of x. So let this thing of x be a property provable about objects x of type t. Then, let me just type this out and then we'll talk about it. Then, this property of y should be true for objects y of type s, where s is a subtype. Hang on. I know, a brain explosion, sorry. Where s is a subtype of t. Booyah. Terrible, right? But actually, it's completely logical. I know this sounds like gibberish, but it actually makes complete sense. Let's do this. Let's first think about it this way. So, what do we got? We've got this important thing. Or actually, let's do this thing. We've got x's. We put these in red. We've got x here. We've got x here. And that's it, right? We don't have any more x's. No. And let's take green, and then let's just say we have y, right? We have y here, we have y here, and yeah, that's it. And then what? Then we have t. I'm running out of colors, this is a bad idea. Let me do it this way. X and y are variables, right? So let me say those are red. So y here and y here. Then we have types, so let me put those in green. So there's the type t here, and then there's the type s here and here. S, and actually S here as well, S, and then there's T here, T, and that's it, right? Yeah. And then let's take blue and make this property blue. So there's this property also, property here, and this property here, and that's it, right? Yeah. So those are all the sort of magic words, right? Those are all the key words. So let's now read this and let's think about it. So here's the thing. What they're saying is that there is hypothetical, arbitrary property, something, right? Let's call it circle. Well, this symbol probably has a name, but who cares? There's a symbol. An object can have this property. So an x, which is any object, it's an animal instance in your object-oriented system. It's an instance of a user class. It's an instance of a resource manager. It's an instance of a factory. It's an instance of whatever you have in your system, right? So x is something. And the thing is that when we say it's an instance of something, right? That something is of a type. So if it's a user, for example, then the user is a type. So user is a class, and then we have an instance. And what we're talking about here when we say x, we're talking about probably collections because it's plural when we say objects. But in order to simplify, let's just think about it as a single thing. So this x represents an instance of something of a type. And in order to talk about all types at the same time, we are talking about t's. This is why we have these two green things. We're talking about t's and we're talking about s's. Right? T's could be the same as s's. Could be, but it could also be different. So T is one type, could be animal, and S is another type, could be music, or it could be any other class, right? I mean, it's general. And then X's are something of some kind of type, it's some kind of instance. And the same goes for Y. Y is also a variable that represents an instance of some kind of class. And then when we're saying that this blue thing, the circle, says that an object can have a property. This might be, let's think about it this way, it could be like responding to the method speak, I guess is what it can be. So if X is an instance of an animal, so its type is animal, and animals have a method which is speak, then this property could be this speak method. So the only thing that this whole mess is saying, right, is that if there is an X, and X has this circle property, so you think about it, classically object-oriented, if you think about classes, right? So T is a class, T defines method, and that means that all instances, if there are instances of T, then that means they have this method, right? This is all we're saying. So X's are T's and they have this property. But they're saying that if that's the case, then it should be the case that all Y's, so another instance of another class, they should also have this property, should be true, right, for objects of Y, if these Y's are of type S, where type S is a subtype. Well, I just realized I'm an idiot. I wrote the same sentence 2 times. So here it says, where S is a subtype, where S is a subtype of T. So I'm sorry, let's just remove this stuff. Where S is a subtype of T. That's right. Sorry for that. So even typing it from the text is super confusing. Anyways, so we're saying that Y's should too have this property if Y's are of type S and S is a subtype of T. Let's throw this in your mind. Let's think about it this way. So you have 2 classes where one class inherits from the other class. So you have the type T and then you have the type S. Should I be green again to emphasize that these are the types? So you have T up here and then you have type S. And so type S is a subtype of type T. It is a T. And the only thing we're saying here is that if there's something that T's do, right? There's some method that T responds to. There's something that T's can do. Then necessarily S's must be able to do that. Subtypes must be able to do that same thing. If not, I mean, why are we then saying that S is a T? And that's the whole point, right? So this is what they're digging down to. They're trying to show us when we should not use inheritance and when we should use inheritance. So if you've got a cat, which is an animal, and animals speak, then cats necessarily speak, right? But if you have, actually this is a very good example, because if you think about it, not all animals speak. And so if we're modeling the whole world, most of the time we're not, which is why we don't have to think about this scenario. But if we are modeling like tons and tons of animals, let's think of an animal that doesn't speak. I mean, snails maybe don't speak, but they're still an animal. So that means that we would be breaking the Liskov substitution principle because we're saying that a snail inherits from an animal, and animals speak, but snails don't speak. That makes no sense. We can't say a snail is this thing, and to be of this thing, you need to have this property. Suddenly this thing that we just created, the snail doesn't have this property. It makes no sense. And that's what they're trying to stop us from doing. So that gives you an excellent way of thinking about inheritance. You have a type, and then you have subtypes of that type. You have some kind of concept, and then you're saying that things can be of this concept. There is the notion of being some particular thing. And some of these things are this thing, right? You have this hierarchy of being, right? Like you could have animal, and then mammals, and then some subtype of mammals. I'm sorry, biology is not necessarily on the strong side, but you realize this whole chain, right? And when you're traversing down this chain, it's super important that whenever you state that something up here in the chain has some kind of property, something up here does something, then everything downwards has to submit to that property, has to adhere to, has to respect the existence of that thing. Has to, so back to their statement, has to be, if this O is a property provable by objects, or about objects of X, then everything down the chain, everything down the inheritance chain, it needs to be provable for all of those as well. Right? Because otherwise you can't say it is of that type. This is really the key notion. And this is, I mean, think about it, this is why we talk about composition of inheritance. Because most of the time, we're really looking for composition. Because we're making 2 general statements. We're saying that, all of the animals can speak, but actually, all the animals can't. And the really dangerous part is, we think think that we have identified all of the subtypes of animals that we will see in our system. And then we get new requirements, and then we realize, okay, actually, we missed a few. And then suddenly we may end up in a situation where we're breaking the substitution principle if we're not refactoring. And this is why we're talking about composition over inheritance. Compose things. Use the notion of has-a rather than is-a. Because has-a is much less troublesome. Right? Of course, when you say has-a, and that thing that you have has its own inheritance chain, inheritance hierarchy. But of course, you still have the substitution principle applied to that inheritance hierarchy. But that's because that's an inheritance hierarchy, right? Just a has-a relationship doesn't have this problem. But yeah, so in summary, the really simple way to think about this is that you have two types. And the parent type, if you state that something is true about the parent type, it has to be true all the way down the chain. If you state that the parent type can do something, all subtypes need to be able to do that. There's a lot more depth to the Liskov substitution principle. This is just part one. In the next video, we will talk about contravariance and covariance. I know, like the strange words just keep on piling up. Contravariance and covariance. And then in the next video, we will talk about design by contract, right? There's some, and this is really moving into this sort of semantics of this substitution principle. So we will talk about things that you might have heard before: preconditions, postconditions, and invariance. So preconditions are things that have to be true when executing a method, for example. Right? Like upon entering a method, what has to be true before that method is applicable. Postconditions are what needs to be true as we exit the method. And invariants are things that always have to be true, like within a class, for example. Like during the lifetime of this of an instance of this class, this invariant rule, this something stated as an invariant can never be broken. And these help a lot when thinking about what this substitution principle actually means in depth. Like when we say this whole thing, let O be a property of X, that blah 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 blah. This whole thing. That's fine and dandy, but there's a lot more nuance to it. And this is what we're going to talk about in these two videos. Possibly I'll do it in the other order because I think this makes a lot more sense than I have to talk about the contravariance. Maybe it's the same. Sorry for splitting this video into two. I ran out of time. I hope this first portion made sense. I hope you now feel like Liskov substitution principle is a little bit less intimidating. Thank you super much for watching. Remember to subscribe, and I'll see you in the next one.
Tired of cold calling? Introducing Lucia, the easiest, most accurate.
Let's talk about Liskov's substitution principle. Liskov's substitution principle is the L in the solid principle, in the solid object-oriented design principles. I find Liskov's substitution principle to be sort of a self-fulfilling prophecy where people tell each other that it's the most difficult principle to understand. And through that, making it the most difficult principle to understand, because nobody actually takes the time to understand the principle. When in fact, the principle is actually really, really simple. So the principle states that if you have a base type and you have a subtype, in other words, you have a base class and you have a class inheriting from that base class, then the subclass should be substitutable for the base class at any point in the program. In other words, in every place where you're using the base type, you should be able to swap that instance for an instance of the subtype without causing any unwanted behavior in the program. And that's it. Right? It's not any more strange than that. It just means that you have an inheritance hierarchy, and as soon as you're inheriting from the base class in a way that makes the subclass not substitutable for this particular base class, then you're breaking the Liskov substitution principle. It's that simple. To really dig into the details, I find most helpful to think about preconditions, postconditions, and invariance. If you're not familiar with preconditions, postconditions, and invariance, don't worry, I'll make another video and I'll link that in the description as soon as it's done. But very simply, preconditions are sort of the entry conditions for the method. To be able to call that particular method, whatever is stated in the preconditions must be true. Postconditions are sort of the other end of that spectrum. Postconditions state whatever must be true when the method has been called. And invariant states what has to be true at all times in the program. So, in terms of Liskov substitution principle, here's how this helps us. Preconditions in the subtype must be the same or weaker. I'll get into what this means, hang on. Post conditions in the subtype must be the same or stronger than the base type's post conditions. Invariance, I find sort of conflicting information, so we're going to have to dig deeper into that some other time. But there seems to be two schools of argument here. Either invariance has to be exactly the same in subtypes, in other words, invariance can't change in the subtype, or the other school of thought seems to be that invariance must be either the same or stronger. Let's first talk about a very concrete example. Let's take the classical animal example. So say that you have an animal, which is a base class, and then you have, say that you have a cat, and then you have something non-animalish, like a box. And I'm just giving this example very silly so that you will really understand sort of the principle. So let's say that the base class states that the class needs to have, or that the object needs to have, a method called walk, right, which will make the instant walk. But for some odd reason, right, in architectural applications features, for some odd reason, you really need the box to inherit from animal. Yes, this is stupid, I know. But because the box doesn't include the walk method, so in that case, what do? Maybe we throw an exception. So throw an exception in the walk method in the subtype box. And this is the problem. This means that the subtype is not entirely substitutable. Box cannot be used in all cases where animals can be used, because box may throw an exception that's unwanted. Of course, everything becomes different if we're actually expecting that exception. If that exception is part of sort of the intent of the design. But let's talk about that some other time. So you can think of it this way. Realize that we're talking about typing, we're talking about subtyping, right? We're talking about something being a subtype of something else. So cats are a subset of all animals, right? Boxes are not a subset of all animals. So to understand the whole precondition, post-condition, invariance thing in Liskov substitution principle, it helps us think about the robustness principle. So the robustness principle states that you should be liberal in what you accept from others, but conservative in what you send. So in other words, that means a method should be accepting when users of the method are sending incorrect values, but it should be very careful with itself sending incorrect values. I think the history of this is from networking or something like this. It's actually a very good principle, and there's this joke that if it would apply to people and not only to programming, the world would be fantastic. Just saying. I'm not at all religious, but it's kind of like a goal, right? So the robustness principle essentially says the same thing as it demands in terms of preconditions and postconditions in relation to the substitution principle, right? So the subclass, a method in the subclass, must receive everything that the base class is expecting it to be able to receive, right? The whole set of possible values. But because it's liberal, right, it may also accept a bit more. So it's the set of all the possible values that it may receive, given that it's the type of the base class. But it's a larger set, so it may also receive some more. The post conditions of the subclass, however, must be the same or stronger, right? And stronger means that it's a subset, right? So methods in the subclass must either return values from the same set, right? Or from the same domain, values from the same set. In other words, the same types of values that you get from base class. Or, if it doesn't do that, it must return a subset of the set of possible values, right? So, in other words, you would never receive anything unexpected from the subclass. And you would never, because you're conservative in what you send. So you would send either anything that the base class sends, or you send something even more restrictive, right? It's also being able to depend on the subclass following the contract, right? To have no surprises. And invariance, lastly. Again, invariance in the base class must be followed, or must be stronger in the subclass. In other words, thinking about sets again, the set of possible states of subclass must either be the same as the set of base class, or it must be stricter. It must be a subset of the set of states of the base class. I know this gets super confusing with all the sets, but if you really start to think about it, it's not actually that strange. So yeah, I can really argue that Liskov's substitution principle is difficult to understand. You just really have to think about it. What's difficult about the Liskov substitution principle, I find, is to actually follow it. Because when you really start to understand that most of the time you're actually really wrong. Right? For subclass is too much. Saying that Liskov substitution principle is bad because it's difficult to follow is kind of like blaming testing for your system being difficult to test. Testing, a system that's difficult to test is an indicator that your system is poorly architectured, so it's highly coupled. Similarly, violation of the Liskov substitution principle is an indicator that your system may be poorly architectured in terms of inheritance. You may be overusing inheritance in places where inheritance shouldn't actually be. That's it for today. For more stuff like this, be sure to subscribe.
Dependency injection, dependency inversion, constructor injection, parameter injection. What does that all mean? Why do we need them? And how do we actually use them? Constructor injection, I find, is one of these things where when you first understand it, you think it's absolutely trivial because you're like, well, I've been injecting values or references through my constructors since like day one. So how is this anything but trivial? But when you then really understand constructor injection, dependency injection through the constructor, you realize that it's massively powerful. You realize that it's not at all the same thing as just casually passing values through the constructor. There's much more nuance to it than that. So let's first get a concept straight. Dependency inversion is an all-encompassing principle. It states that you should invert the dependencies. So you invert the relationship in a way that might seem unnatural. Dependency injection is the specific act of inverting a dependency. Constructor injection is when you're performing dependency injection through the constructor of an object. And parameter injection is when you're performing dependency injection through the parameter of any function of an object. So stated in the most simple sense I can think of, instead of considering the formal definition, I would think of it this way. Dependency injection is about never coupling to a concretion, but always coupling to an abstraction, right? Obviously that's oversimplification because at some point you have to create a concretion, but we'll return to that in the end. So the point of performing dependency injection is that you want to be able to change your instances of classes at runtime and not only at compile time, which essentially means that you can change behavior of your program at runtime and not only at compile time. And which also means that even at compile time, you can change the behavior of your program without rewriting classes, but instead by writing new classes and then injecting those members instead of rewriting the old ones. So dependency inversion increases the flexibility of our code. It increases reuse, right? It encourages small classes with limited responsibilities, and it makes it easy to exchange one instance for another instance in order to change particular behaviors. That's one of the aspects. The second aspect is testability. Without dependency inversion, testability or unit testing, isolated unit testing would be really tricky. Because when you want to test in isolation, you want to test a class without integrating with other classes. So in that case, instead of allowing your class to integrate with other classes or allowing your object to interact with other objects, you inject a lock that you have full control of. So you use dependency injection, which is possible because you have used, because you are designing according to dependency inversion, and inject a class that, or an object that you have full control over, which means that you can A, test in complete isolation, and B, because of that, avoid unwanted things such as random numbers in your tests, for example. Just imagine if your tests would pass 50% of the time, fail 50% of the time. Probably tricky, and we want to avoid that. How do we actually do dependency injection? So I'll only talk about constructor injection because I think when you see how constructor injection works, you'll trivially figure out how parameter injection works. So imagine that you have a class called animal, and imagine that you have a bunch of animals inheriting from that class. So we have cat, we have dog, we have cow, etc. Imagine then that these classes have an instance method called speak. And this instance method doesn't really matter what it does, but let's say it prints some strings. So the cow says moo and the cat says meow and etc. So naively, we might hard code this behavior of either saying meow or saying moo into the speak method, into the specific classes, i.e. moo would be in the cow class and meow would be in the cat class, etc. This is sort of object orientation 101, right? This is what you learn in class. Of course, in a bigger system, if it's not about saying moo, but it's rather about something very complex. So assume essentially it's a bunch of more code. So then I think, okay, let me put this behavior in another class. So perhaps you have cow speaking behavior, dot speak, and you have cat speaking behavior, dot speak, and so forth. So we now have two hierarchies. We have animals and we have speaking behaviors. Okay, so this is all fine and dandy, but the problem is that we are potentially breaking dependency inversion. Let me explain. So if the cat instantiates the cat speaking behavior and the dog instantiates the dog speaking behavior and so forth for the cow, then we are breaking the dependency inversion principle. Because the higher module, i.e. the cat and the dog and the cow, is coupled to the low-level module. In this case, the speaking modules. So dependency inversion says actually you should invert these dependencies, such that both the high-level module and the low-level module should both depend on abstractions. The abstractions in this case are the parent classes. So for both of these hierarchies, the parent class for the i.e. animal and the parent class i.e. speaking behavior. Not the concrete speaking behaviors, nor the concrete animals. So the dependency inversion principle in this case essentially states that animals should not be coupled to concrete types of speaking behavior, but rather to the abstraction. So this means that we want the animal classes to not instantiate their own speaking behaviors, but rather that they somehow should receive a speaking behavior and then run the method speak on that speaking behavior. How they would receive that would be through either constructor injection or through parameter injection. And the point here is thus that whether the animal class, i.e. cat, or etc., then only knows about the most abstract, or the abstraction, speaking behavior, and doesn't know about concrete speaking behaviors such as the cat speaking behavior and the cow speaking behavior, etc. The most interesting point, or the most interesting benefit about this design, I find, is that oftentimes you realize that actually you don't need subtypes. Actually, in many cases, dependency injection is enough and you don't need inheritance hierarchies, which is probably why people are saying composition over inheritance, right? Because you can compose what behaves as your subtype instead of actually constructing your subtype. In this particular case, assuming animals do nothing else, then cat and dog and cow would all contain the same code. They would just have different names, which makes them completely redundant. So in that case, we only need animal. Thus, this is how we've achieved composition over inheritance, because we only have one animal class, and when we want to construct a cat, we can instantiate a cat speaking behavior and provide it to the animal class. Thus, the animal instance will behave as a cat. Similarly for cow and for dog. So if you take dependency injection sort of to its extreme, in absurdum, then you will realize that you can always inject dependencies instead of instantiating them. Which is, think about this, also why people say that the new keyword is dangerous. You should always be wary when you see the new keyword. Is this really the correct place to couple to a concretion instead of an abstraction? So using dependency injection, you can always defer using the new keyword. You can always defer instantiating upwards, backwards, out of the system, right, towards the main of your program. And this is actually what happens if you use dependency injection in madness, right? In some sense, you could instantiate all of the players in the main of your system, and then have no new keywords in the rest of your system. But of course, there are always trade-offs, and I would actually say that a little bit of dependency injection is better than no dependency injection. A little bit of inversion is better than no inversion, which you'll discover when you, for example, try to test your units in isolation, or when you try to quickly respond to new requirements without constantly having to change all the code. So that's dependency inversion. Please ask any sort of questions that you might have in the comments, and subscribe for more.
Hey, you want to get leaner, stronger, learn some cool calisthenics, bodyweight skills, but right now you may need to
If I'm understanding the open-close principle of the solid principles correctly, then I think in extension, or in its extremist form, it's saying that you should never have to rewrite any of your code. You should only write new code. You should never rewrite your existing code. You should only add new code to your code base. This is of course a kind of profound statement, and I understand that it seems unreasonable, but I assume that you also see that if you were able to do that, then it would be easier to avoid bugs in code, to avoid problems that evolve over time. For example, you would never run the risk of changing a particular piece of code, thinking that it's not used somewhere else, and realizing that it's actually used somewhere else, and then breaking that piece. So I've been thinking a lot about this lately. I mean, how could you possibly never have to rewrite code? So let's talk about this beyond the open-close principle. Let's say that what we're trying to avoid is rewriting code. So let's say that the actions that we can do is that we can add new code, right? We can add new classes and modules, but we can also delete code. We can also delete classes and modules. This means that if you want to change something, you have to delete the old one and insert a new one. And we're not talking about chunks of code, right? Because again, chunks of code is risky. Then it becomes easier to think about if you think about dependency injection. This is possible through dependency injection. So instead of writing, for example, large monolithic classes, and instead of instantiating your dependencies within a module, right? Instead of a particular module or class having to know about its dependencies, it instead takes parameters of types, where the types could be duck type, right? It instead takes parameters of types that perform particular roles. This means that if you need a new thing to play the role, you simply instantiate a new thing and inject that new thing into wherever you were using the old thing. And this is the key to understanding how we stop rewriting code and instead only write new code. So if you think about it, it probably makes a lot of sense. If you have a sorting method, for example, instead of hard-coding a particular sorting algorithm in that sorting method, you instead, in a functional language, you take a function, or in an object-oriented language, perhaps you take an object that plays a strategy role. You take a strategy object that has a sorting algorithm, that uses a particular sorting algorithm. If you do that instead, then you can simply, if you want to change your mind later to a different sorting algorithm, you can simply inject another object, a different object that utilizes a different sorting strategy. Which means that at the point where you want to change your mind, where you want to change from one sorting algorithm to another one, then you won't actually have to rewrite code. You simply have to create a new sorting class and then inject that member instead. But if you're paying close attention, you would of course quickly realize that when I say inject the new one instead, that of course has to become a rewrite, right? Because yes, you create a new member that you want to use, but at some point you have to put that new member into the existing system, right? Into the existing object graph. And then it has to turn into a rewrite, or no? What's interesting is that even then you can avoid a rewrite by simply rewriting upwards, rewriting whoever was using that thing. So if you think about it, at the point where you are in fact instantiating a thing that you are injecting somewhere, at that point, that is also something, right? That is also an object. That is also part of some kind of class. If that isn't injected, right? If that's injected, you just move up the chain. But if that isn't injected, then you have to rewrite that, right? But again, the rule says don't rewrite, write a new one, right? So you write a new one of that, of whatever that is, right? You write a new one of that, and then inject that to whoever was using that, right? So it's kind of a question of dependency injection into matters. Like, I've tried this out for some time now. It's entirely possible. It's completely possible. When you want to change something, right, you simply write a new member, find out where you need to inject that new member, inject that new member. And yes, then I would pragmatically say, like, if that rewrite doesn't cause, if I'm sure that that doesn't cause any interoperability conflicts, right, any conflicts with other pieces of code, then I would simply rewrite that. But if I can't rewrite that, then I would definitely go up the chain and say, okay, let me write a new one of these things who are using the thing I just wrote the new thing for, right? Let me write a new one of these as well, and then upwards. Then let me write a new one for that, and then write a new one for that, etc., etc., etc. Until you have sort of a new main wrapper for your application, right? At some point you can probably stop and say, okay, pragmatically, I have enough control of this piece, so I don't need to rewrite upwards, I can just rewrite here, right? But that would be a significantly safer rewrite than rewriting the small pieces down in the application. So to sum up, I think it's entirely possible to avoid rewrites altogether. You can simply get along with only writing new code and deleting old code. And then I don't mean as in deleting a chunk of code. I mean as in writing a new modular class and deleting another modular class. That's it. Thanks for watching, and I'll see you in the next one. If this was super confusing, by the way, please let me know in the comments so we'll dig further into this.
The other difference is between the salesperson who's supposed to go left and right, and the one who can't close to save their life. So it's not some fancy line, but just...
Let's briefly talk about the interface segregation principle. The interface segregation principle is one of the solid principles. In other words, it's the I in the solid principles. I find on one hand it's the easiest to understand, but on the other hand, one of the more difficult to understand because it's so easy, so it's confusing. It's like, is that all there is? But it's probably that it's not necessarily obvious what the value is with the principle before you really start to apply it, and then actually really see the value. So the interface segregation principle says that it's better to have many small interfaces rather than a few very large interfaces. Or if you restate it just to remember it easily, too many is better than too few. But what do we mean with small interfaces? Let's as usual look at an example, and let's take the classic animal example. So assume that we have an animal class. Say that we have instance methods for the concepts of eating and for, say, moving around, and say, for sleeping, for example. So in other words, we have three behaviors that the animal can perform, and we call these methods on an instance basis. So we have an instance of an animal, and then we call, for example, sleep on the instance of the animal. The interface segregation principle is of course highly dependent on your particular context and your particular requirements. So in some sense we can't apply it now because we don't have requirements and just making up an example on the fly. But stick with me because I think you'll sort of understand what I mean. But again, remember that it's highly dependent upon the requirements. So it's not necessarily so that in two systems, small mean the same thing. In two different systems, small mean different things. But back to the example. So the interface segregation principle, in this case, would say that we should not stick the sleep method, the signature of the sleep method, the signature of the eat method, and the signature of the move method into the animal interface. Because we are then constructing a large monolithic animal, when we could in fact instead be creating interfaces for smaller roles, and then give all the necessary roles to an animal instance. So what would an alternative be? An alternative could simply be to take all of these methods and create one interface per method. So in other words, we have a can eat interface, we have a can move interface, and we have a can sleep interface. And in other words, that means that the animal isn't necessarily an I animal, right? It doesn't implement the interface animal, but rather any particular animal implements the interfaces can move, can sleep, and can eat. But what would be the benefit of doing this, you may ask? One benefit, generally speaking, by creating small interfaces and separating out different roles and responsibilities, we are favoring composition over inheritance, and we are favoring coupling over coupling. If you think about microservices, it's much the same thing. Instead of creating one giant monolithic app, we are creating a bunch of small responsibilities and then composing them together in the way that we want to use them. But let's talk about something more hands-on. Now, it's kind of silly because in the example I chose, probably all the animals we can possibly conceive of will be able to, in some form or another, move and eat and sleep. Probably. I mean, not of it, right? But say that we are building some kind of animal simulator, or we are building some kind of game, right? With this design that we currently have, with all of the small interfaces, if you would want to have other species, such as plants, for example, say trees, then those couldn't necessarily move, and previously they had to be in a different inheritance hierarchy than the animals. But if we separated the small interfaces, so that if you remember we have can move and can eat and can sleep, maybe it would be reasonable to say that trees, that some species can, for example, eat, but they can't sleep or they can't move. So trees can't move, trees can't sleep, but trees do have some kind of metabolism. They too consume energy and produce waste. So it might seem contrived, but the point I want to make is that when we are favoring composition, when we have small roles that objects can play, it's much easier to design new objects without having to make entirely new classes. So that's it. That's most of the stuff you need to know in order to get started with the interface segregation principle. Again, remember, it's better to have many small interfaces than a few very large ones. Or, stated super simply, too many is better than too few. So thanks for watching, and as usual, if you have any questions or comments or angry outrages, do hit them up in the comments. And apart from that, if you want more code videos like this, be sure to subscribe. Let's talk about data clumps. Data clumps is a code smell. And remember, a code smell is an indicator that something may be poor about the architecture of your code. It's not necessarily that it definitely is poor, it's just an indicator that it might be. So what are data clumps? Data clumps are when more than one piece of data is oftentimes found together. Martin Fowler gives a great example. Imagine, for example, that you have a start date and you have an end date, and you find these two pieces in your application oftentimes together. In other words, it's not that you're at some point in your application only finding the start date or only finding the end date, but usually you come in contact with both of them at the same time. You have a start date and you have an end date. That would imply that you can probably extract an object that contains both of these two things. So instead of passing around the start date single-handedly, and instead of passing around the end date single-handedly, we pass around a date range. Ben Orenstein also employs this particular example in a great talk called Refactoring from Good to Great. I'm linking that in the description, so be sure to check that out. I think he also explains it very nicely when he says that a good way to identify a data clump is that when one of the pieces do not make sense in isolation, but only make sense together. That's when you know that you have a data clump. So again, think about the date range example. Only a starting date makes no sense unless you have an ending date as well. But of course, again, code smells and not necessarily always problems. So of course you could have a start date without an ending date. Hypothetically, it could be that the ending date is infinite, for example. But this is purely hypothetical. So data clumps are when more than one object is usually bound together, which then implies to you that you could probably extract a new object and put these pieces into the new object. So to make these pieces members of the other object. Another example of a pretty clear-cut scenario would be if you find first name and last name passed around oftentimes together. That would imply that you are probably missing a user object that would encapsulate these two properties. But now we're talking about very obvious scenarios. Let's talk about the scenario that is less obvious. What if you, for example, find a user and a credit card at the same location? Spontaneously, this doesn't feel like a data fund. Even if they are passed around together, it might feel like they're totally different things, and thus shouldn't be coerced into one object, or rather encapsulated and had within a single object. But it entirely depends on your application. If you're in a checkout process, and for example, this is the decided credit card and the decided user, then perhaps it does make sense to pass them around together. If you think about the term payer, for example, then suddenly it makes a lot more sense. It's not a user, it's not a credit card, it's not a user and a credit card, it's a payer for the particular card. And that kind of makes a lot more sense. So just because it doesn't seem like an object spontaneously doesn't necessarily mean that it's not an object. Give it a serious thinker and try to describe the plum using one word. If you can find a word that does describe the plum pretty well, then you're probably looking at something that wants to be extracted into an object and not kept as separate pieces. Let's just mention what the benefits of this would be. So, for one, the benefit is semantics. So it's easier for a reader of your code to understand what they are dealing with if they have one word. Because they then understand that these two things are two pieces of one thing and not two completely separate pieces. And they have a name for that thing. That's particularly evident in the Ben Ornstein case, where you have starting date and you have ending date. It's suddenly a lot easier to understand what's going on if you're talking about a date range. Lastly, we'll discuss this in more detail some other time, but generally, because of coupling, fewer arguments to method is better than many arguments. So you are coupling to less things if you have fewer arguments. So coercing pieces of a data plumb into a single object reduces the number of parameters that we have in our methods, which from a coupling perspective ought to be a good thing. Hey, Anthony, first things first. Sorry about being late. I just now realized that you had in your question actually requested that if it's possible that I please answer before such and such a date. And clearly we're beyond that date, so apologies about that. Here's what we're going to do. I will put my email in the description of, or the message that follows along with this answer to your question. So if this answer comes too late for it to be useful for you within the context that you were asking the question, send me an email and tell me that, and I'll talk to Scale about it and make sure that you get a refund, right? So hopefully that turns out right. But anyways, that's a precursor. No, not a precursor. That's the prelude. But let's get into the actual question. Okay, great question. Okay, so essentially you're asking about an IoT, like an Internet of Things kind of system. And I haven't really thought this through thoroughly, but I figured we'll just take a stab at it because I think you've outlined the issue or the scenario pretty well. So I guess we'll find, I think we'll be able to find a few useful points as we go through it like this. So let's get started. I mean, let me just try to reiterate what you've been saying. Right? Let me sorry, just move the screen so I can actually see it from here. So you're saying, okay, you'd like to follow the object-oriented programming principles and the solid principles, and you're building something which is like IoT-like, where you have, and this is like, I think it's called something like a noun and a verb analysis or something like that when you're doing object-oriented modeling. And it seems like you're actually already doing that, right? You're saying, okay, we're going to have devices, we're going to have sensors, so these are nouns, so English nouns. So it's basically an IoT system where devices can be controlled and sensors can be displayed and analyzed. So I should say devices and sensors, and devices can be controlled and sensors can be displayed and analyzed, okay? And you were saying, you were thinking about design patterns, you were thinking about facade, command, strategy, and observer. I think this is a great set of patterns. Like, let me just jump into it at once. I think about facade pattern as something that I apply in retrospect if I've already managed to design the inner workings of a subsystem, or let's call it a module, right? So if I've been able to wire the pieces together of something that does something complex, and then I think, okay, well, this is unnecessarily complex, this is very abstract and very general, but it's unnecessarily complex for the person who wants to use it. So if I'm in that scenario, then I would think about creating a facade. But I think it's, in my mind, I mean, people probably have varying opinions, but in my mind it seems unnecessarily, let me put it this way, it seems potentially dangerous, very much quotation marks, potentially dangerous to start in the end of a facade, right? Because then you're oversimplifying your scenario, and you're painting yourself into a particular simplified corner, which might not necessarily be the particular corner that you want to build your abstraction in. To me, this is kind of but I think you're kind of simplifying it. It's like, start by first figuring out how the problem needs to be solved if you solve it sort of quotation mark perfectly, and then figure out the simplification, right? Rather than starting with the simplification and then finding that when you realize what the real solution, what the perfect quotation mark solution would look like, it might be very difficult to retrofit the perfect solution into your simplification. So that's what I'm thinking about facade. So I would push that onward, right? And also, we put it this way. Sometimes we don't even need the facade, right? Because sometimes it turns out that the perfect solution that we're building is sufficiently simple so that the user can use that instead. Okay. But anyways, I mean, it's a good time to bring up in this context. And this is a strategy pattern. Like, I mean, strategy pattern is, in my mind, essentially dependency injection, dependency inversion, or I should say dependency injection. So, inevitably, you're going to use it, so spot on. I mean, for sure, you're probably going to use strategy pattern. What do you think? And then you think, okay, looking for some interfaces after classes, maybe some concrete classes. Right, but, and then you're thinking about dividing a house into room objects, and then each room object have devices and sensors. And spontaneously, think about this. First of all, I mean, great suggestion, great suggestion. I think this makes, like, overall, the way you've structured your thinking here, or sort of, let's say, pretty sure that the initial modeling interest, I think is great. I mean, this is a very good point to start from. Okay. Dividing a house into rooms. This is an interesting scenario, right? I'm not going to push towards that when we start to draw stuff now, but just think about this. It's possible that you could even use composite pattern. So, for example, I think I've talked about I have talked about this in another video, which might be the command pattern video, maybe. In that video, I talked about how we have Philips Hue in our home, right? The Philips Hue light system, and for example, we have these controllers to control the different lights. And something that bugs me is that one of these things can control, of course, there are third-party solutions for that and all that, but I'm just to emphasize the scenario. One of these things can control a room, right? Or it can control up to 3 rooms. So you can connect it to 3 rooms at the same time, or you can connect it to a single room. But I can't connect it to subsets of rooms, right? So I can't connect it to, like, I'm going to have, like, section 1 of the room and section 2 of the room. And I'm going to have one controller that controls section 1, one that controls section 2, and another one that controls both, right? Then I have to make them actually separate rooms, right? Which metaphorically doesn't really make a whole lot of sense, right? At least in mine. So yeah, maybe you could say, okay, well, I'm just using this Philips Hue stuff incorrectly, and I should just figure out and say, okay, I'll call this, like, an actual room, and I'll call this part an actual room. But I would think of it this way. I would think, what if we just think about it as composites? What if we just think about the room as a set of devices? Yeah, it's a set of devices, right? Where this set of devices could be either a set of devices or sets of devices and other sets of devices, right? You could say, a room is just a section, right? So you have section A, and then you have section B, and then you have the whole room, which is section C, and section C is comprised of section A and section B. And then you could say that a house is section B, and section B is comprised of section C. right? And section C is comprised of section A and B. Yeah, sorry. I'm confused about the letters. But I think you were saying what I'm saying, right? It's like we would be doing this like, well, the house is comprised of section A, sorry, now I'm using different letters. So forget about previous class, right? So let's say the house is comprised of the living room and the bedroom. The living room has section left and section right. Right? Let's say something like that. And TV area, or whatever, dining area, and relaxing area. Yeah, it seems like easy. Okay. But then you could even continue this and divide further so that the left area is divided into the top left area and the bottom left area. So, sure. I mean, I assume that one of the reasons that they didn't do this for you is that maybe it's unnecessarily complicated for the average user who probably isn't looking for this level of granular control. But I'm drawing this parallel. And likely your scenario to this scenario, because maybe that would be interesting for you, potential, right? Because it depends on what you're building. Maybe you want to be able to work with sort of arbitrarily detailed sets of devices and sensors, right? Or arbitrarily aggregated sets of devices and sensors. So maybe you would look at concept that. Okay, but let's just remove this one. Alright, but yeah, let's get into this. Okay, so in the interest of time, I have to do super quick. Devices and sensors. Let's just start with this, right? Let's say we have devices and we have sensors. And in my mind, it's not obvious yet that we need classes or interfaces for these because we're not sure what the methods for these would be. Right? So let's hold on to that. Let's instead just think about, okay, what would be the examples of devices? So since we're talking about consumer, let's say that device would be a lamp. Right? Actually, you have some examples. Heating, refrigerator, vacuum cleaner, right? So let's say heating. It's called a thermostat, right? Wait, what is that? Yeah, I think so. So apologies if I'm getting this word incorrectly. So this is the issue of looking at anything. So I think this thermostat is something that can control temperature, but also can measure temperature. But yeah, so no, side note. Okay, that's not just as you were saying. Let's call it heater. Okay. And so there are lamps, there are heaters. Maybe there is, as you were saying, there's a refrigerator. Maybe there is I don't know, like let's say a wall plug or whatever you call it, like a switch, right? And I don't here mean a switch as a router and a switch, but I mean as a wall plug switch, like a on-off plug. Maybe there's nothing like that. Okay, so that's that. And what are sensors? And by sensors are stuff that gives you data, right? So, say motion sensor, you're saying motion sensor, smart thermometer. I'm not sure what the smart part here is refers to, I'll just say thermometer. Okay. And more stuff like that, right? Like, we can go into that. So initially you might say, okay, well let's just create a hierarchy, and this is kind of the old school object-oriented way of thinking. Right? Like, let's create a hierarchy where it's like a taxonomy, right? Where it's like this thing derives from this thing, which derives from this thing, which derives from this thing, and that's how we're sort of showing what things are in there. But that has a number of different problems. I think you know that if you watch my strategy plan video where it's like, well, sharing behavior like this and this is fine, but when you have to share behavior like this, you get into troubles. mean, that's not the correct way of drawing it. It's like if you have maybe this is actually more accurate. It's like, well, this thing shares behavior from A and shares behavior from B. It's like it has two parents, and this thing shares behavior only from B, for example. That's another way of thinking of it. So, let's do this some other time. I need to restructure my problem and sort of follow the conventional way of talking about this problem. But I'd recommend Sandy Metz has great videos on the issue of where she really explains like the issues of inheritance and why some problems can be solved using inheritance. Okay, so what we're going to do instead is we're going to talk about interface. So I would say, like, let's just follow down the path of experiment. So I would say, let's figure out what's common between these different things, and then let's give them an interface, right? Let's call them something. So, something, I mean, a switch is kind of often on-offable, right? You can call that something. It's called powerable, right? So let's say that there's an interface called powerable. Okay? What does that say? It says, well, you can switch on and you can switch off. You could have a switch in this. You could have a switch, actually, let's give it that as well. So there's a switch function as well, and maybe that would even be abstract. So this would maybe be an abstract class. Switch already has an implementation because switch calls on if it's on and off if it is off. But then it needs to be able to inspect. Yeah, so let's get that. Let's just say on and off. Okay, that's fine. Yeah, so I'm starting to realize in my mind that this is a non-trivial scenario. We're really not going to be able to fit as much stuff as I want in this video, but let's see how far we get. So we have something like on and off, okay? One methods. Powerful. So this is powerful. But actually, a refrigerator is powerful, a heater is powerful, and a lamp is powerful. Cool, right? You can cut the power. Okay, so let's say we have a lamp. Yeah, actually, let me save some. I'll see if I'm doing this. Okay, so who inherits or who implements the interface powerful? Well, lamp, heater, refrigerator, and switch. They're all powerful. Cool. Okay, those are the devices that are powerful. Let's think about them all. Because a heater and refrigerator has temperatures. So you can set target temperature. So let's say temperable. And I am completely aware that's not a word, and if it's a word, it probably means something else. So let's say maybe we just have set, right? And it takes let's pretend to have a data type, which is a temperature, and I'll call it temperature. Right? So you send some kind of temperature to it, and you set that temperature. Now the question is, okay, who implements that interface? Well, actually, we probably use a different code because it's a bit tricky to see. So, temperable, heater and refrigerator is temperable, right? So, refrigerator and heater. And lamps really making sense, right? I mean, lamps are not temperable, switches are not temperable. Switch probably only does on-off, right? But what about the lamp? Let's say that we have these sort of hue lamps, right? Like let's say we have colored lamps, or lamps that support multiple colors. Then we need to control colors, right? So maybe then let's see what colors. So let's say let's call it colorful. Colorful. So things that are colorful. And then we can say let's also have here a set, but here we set, and we'll pretend we have a color data type, so we'll send a color into the set method of something that is colored. When this is interface, and who implements that interface? Well, it's actually just the lamp. Okay? Heaters are not colorable or colorful. Refrigerators are not colorful. Actually, let's call it colorable. Color, because it's countable, colorable. No, colorful. Colorable. Okay? So the lamp is colorable. That's cool. Okay? Then we go on like this. And then there's necessary overlap between the different things, and it's because of this overlap that we can't build a hierarchical structure for this whole problem. Okay. Now, let's talk about the sensors. We can do the same thing for the sensors, right? So the motion sensor, let's think about that. Or wait, we have to do the same thing for the sensors. So the sensors need to be able to report data. I think you were spot on when you were saying that you need to say that the sensors are observable so that you can observe, you can register observers to them, and then whenever they have new data to report, they would report that data. Yeah, so it's not obviously yet what you need to say that the motion sensor is of something, the thermometer is of something, except that we would maybe say that it is, actually, so this is maybe the sensor part, right? So let's say that the sensor interface is that you need to be able to add a sensor observer, and you remove a sensor observer, remove and potentially notify, but let's assume that notify happens internally. So now we're thinking about this. So this would be the observer from the design management, right? The sensor. So the sensor is observable. And then we need to be concrete observers. So we say motion sensor and thermometer are both observable, so you can observe them. Okay? That's cool. What do they report back? Right? When you say, let's think about this, is that actually part we get that right on the type level? So yeah, so let's say so let's just get a type check. Maybe we would say something like this: sensor, and then we have a sensor observable. Sorry, then we have a sensor observer. But these are, so actually it's here. So sensor needs to be able to say, get state or something like this. Right? And the question is what the return type is of this. This way. So the add method here and the remove method here are both void methods, but here we would have something that returns, let's say sensor data. And then we say get data. Or something like that. Get state or something like that. Sorry, my captain's getting out. So we get back some sensor data, and then it's a question of like, what is sensor data? So sensor data needs to be a different type, and what does that do? Well, the thing is that thing, that's like, let's think about this. This is going to have to be the thing that's the same across all different types of sensor data that you can get. Similarly, we might want to have something which is the same across all the different devices that we have. But we haven't gotten to that point yet, so we're not entirely sure what that is. I'm not entirely sure what the sensor data is going to have to be, and I think here we might actually want to use homomorphism as in, but I mean, of course, yeah. Yeah, I was going to say my font using active circuits. Leave that around. Let's push that off. You're going to run out of space here to see that. Okay, so looking at, we have these devices. We've started to think a bit about the sensors. And we started to think a bit about the observer. And so we're saying that there are sensors that are observable, and when you observe them, you get some data back. And let's now think about the controlling part of the device. Right? So you're saying maybe you need the command line. I think that's a great suggestion, right? We need to be able to use commands to send commands to these different devices so that they, and assume that they invoke the commands that you send them. And here's, I think this is a pretty interesting moment because I thought a bit about this before and I started to think of, okay, depending on how you want to be able to run your commands, like let's say, let's think about the room diagram, right? So you talk about, well, maybe there's a room lab structures. Now I'm not going into this whole different kind of stuff that we talked about before, at least. Yeah. So if the room contains some kind of devices, right? It has a relationship device that sort of aggregates devices. And the question is there a single type called device in which you bundle lamps, heaters, refrigerators, and switches, right? So if the device is a collection of some sort, does that set of devices, are you mixed together, or do you separate, let's say, powerful stuff from temperable stuff, from colorable stuff, and keep these in different lists or collections, right? So like, room contains all the powerful stuff here, all the colorable stuff here, and so forth. That is a much easier problem, right? Because you're not going to have to think about it as like, the visitor pattern is designed to recover most type information, right? I mean, that's like, it's a profound statement because that happens all the time. So you take different stuff and you throw that into a collection and say, well, I used to know that this is something that's powerful. I used to know that this is something that's temporable. But now I'm just throwing them into a collection where I refer to them as devices. And suddenly you lost the type information and somehow you recover that type information. Possibly, right? You may want to down the line. So that's why if you keep this effort from the beginning, it's going to be easier because you haven't lost the type information, so you won't have to recover it later. But you probably want to put them in the same list, right? Probably because there's a massive overlap between these different things, and constructing the rule might be tricky. I would assume, I'm not sure, but I think it might be tricky if we do it this way, where we sort of have to know what type each different thing is. And in some sense, it would then be easier from the outside perspective, like from the room as a user, or the one who's constructing room, from the perspective of that thing, it would be easier to just treat them all as devices. So then it's interesting because then we can say, well, actually, there is this thing called a device, right? And we're not entirely sure what that is or what it does yet, right? But there's something called a device, and all of these things are devices. Lamps are devices, heater devices, refrigerators are devices, and switches are devices. Okay, we're not sure what that. We're just saying, okay, a room contains devices. Okay, so you have this collection of devices. Now, how does the user construct a command? Like let's think about it, right? It's like I'm opening like the FitQ app, and I'm scrolling through, or let's not think about FitQ. I'm opening this smart app that you're building, and I'm scrolling through my list of devices, and they're completely different devices, which I can see from the names, for example. Right? I have this living room lamp, I have this somewhere living room heater, let's say. Right? I want to send commands to these, but how do you display different commands, like fundamentally different commands, qualitatively different commands, like on the type level different commands to the user? How do you do that? Right? So probably, here's the way I thought of it. Probably each device needs to be able to somehow tell, when asked, it needs to tell you or give you a way of constructing commands for that device. Something along these lines. Probably something along these lines, right? So, of course, the alternative to this would be type checking. Of course you do this with type checking, but we're trying to solve this using object-oriented principles, right? Without doing type checking, right? We're sorting type checking. We're trying to use polymorphisms, okay? So I think this is probably a scenario of the abstract factory pattern. So a device is so a device, I should put it this way, a device can give you a factory, where that factory is part of the abstract factory pattern. So it gives you a factory that produces commands for that particular device, right? So in other words, when you ask, so let's say, I think this is going to have to be pluralized. Let me say this in plural. Get factory, okay? And it's going to return a collection, I'm not going to write this, but it's going to return a collection of device, of command factories. So let's say there's also a type called, there's also a type called a command factory, right? Which is something that can produce commands. So, sorry, this is standard when I get going. Like, I'll keep going on the movie. Okay, let's keep going. So, part 2. So these devices are